Sharing the wrong slides. One moment.
Oh, no worries. I'll do
There we
the
go.
introduction in the meantime. Perfect. All right, so thanks everyone for joining us today, and I hope you all had a great week and a great summer. And I would like to welcome you for the first Tea Talk of the session, which is going to be a Prof Series Tea Talk. So, for those who are new to the concept, the idea behind the Prof Series talk is to have Mila Prof share his or her own research interests, and we do that approximately once a month. So we had a few of those in the past, and usually it's either an overview of the research done in the prof's lab or what's next kind of talk. And so, yeah, it's done usually once a month, but because September is more of a onboarding month for the new students, we decided to have the first 4 Tea Talks of the session to be Prof Series Tea Talk. And today it's even more special because it's the back to school Prof Series Tea Talk. And we don't have one, but 3 amazing speakers who will give short spotlight talks of about 15 minutes. So the way it's going to happen is that we're going to have a sequence of spotlight talk, small Q&A period, like really 5 minutes, so 1 or 2 question maximum, then the next talk and so on. And after the third and the last talk, for people who wants to ask further question and make some other comments, you can stay connected and do so in a more informal way. In order to ask your questions, as usual, you just have to type the word question in the chat or I have a question, and I'll let you directly ask it. Of course, in order to ask your question, make sure to unmute yourself and then mute yourself back when you're done. All right, and yeah, so the order of the talks, as it was indicated in my previous slide, will be Blake, then Irina, and then Daniel. The order is completely random, guys. All right, so whenever you're ready, Blake, the floor is yours.
Great. Thanks very much, Rem. So I'm going to be talking to you today about a very new project in my lab. We've been trying to understand how bias and variance in the brain's gradient estimates might actually affect real learning in the brain, and I'll unpack this for you a bit now. So let's start with, can I actually advance my slide? There we go. Gradients in the brain. For those of you who are unfamiliar with me and my research, that might be a natural question that you would ask. Why would we even be talking about gradients in the brain with respect to loss functions, that is? And the way that I'm going to motivate this is by taking the following perspective. So, what does it actually mean to learn? Well, learning necessarily indicates that you're changing somehow. You're physically changing, in fact, in your brain. But it also necessitates a normative perspective. You can't just change, you have to change in a way that makes you better somehow. Otherwise, it's just change, it's not learning. And to quantify this normative perspective, in machine learning, of course, we use loss functions, but we do the same thing in computational neuroscience as well. So we have some function over the parameter space, which we might think of as synaptic strengths, for example, and we're interested in descending this loss function in order to go from worse to better. Now, if loss goes down over time necessarily, and you're making relatively small changes, which is indeed what happens in the brain, then the changes in your synaptic weights must be in part in the direction descending the loss gradient. So if you consider some path taken by the synapses through synaptic space over time, and you look at the direction of that path across that time jump, it can't be totally orthogonal to the direction of your loss gradient. It has to, even though it might have some orthogonal components, it has to at least be partially aligned with it. And although brains must therefore partially follow the gradient, since we do get better at stuff over time as we learn, it is unlikely that they follow it perfectly. I mean, no algorithm follows it perfectly likely. Even when you do full gradient descent without batches, you will still have some off estimates as a result of digitization, for example. But in the case of brains, this is going to be more pernicious. Due to both the constraints and the noise inherent in biological systems, it's pretty much impossible that brains will be able to directly follow a gradient or even get super close to that. Now, we can think of this in terms of the learning algorithm, in terms of this equation here, in a learning algorithm agnostic manner. So when we consider the weight changes at any time step t, there's going to be some component that's in the direction of the gradient, and then we can characterize the bias and variance by saying that there's some component that's just always pushing the weights in some constant direction, the bias, and then some component that is sampled from white noise, for example, and which adds just some noise to the estimates. Now, what we'd like to know in our project here is, regardless of the specific learning algorithm that a brain uses, what would be the impact on learning of bias and variance in the brain's gradient estimates? So just as a little recognition here, the work that I'm about to show you was done by Arna Ghosh, a PhD student in my lab, and a newly minted Vanier scholar. He's probably embarrassed to have me say that, but whatever, I'm like a proud dad, so deal with it, Arna. And yeah, so let me tell you about what he's done. So we're going to use a teacher-student paradigm for the empirical tests I'm going to show you here. I'm also going to do just a tiny bit of math to get intuitions for what's happening. So in the student-teacher paradigm for our empirical tests, what's going to happen is we have some fixed mapping determined by some neural network that we just set the weights for, frozen. We're also going to provide the same inputs to that fixed neural network and the neural network that we're going to train. We look at their outputs, and the error then is just the difference between these two. And of course, we use our learning rule to update the neural network that we're considering. Now, a bit of preparation for the bit of mathematical analysis we're going to do. So as I mentioned, we're going to have an algorithm agnostic way of characterizing this. So we just say that there are changes that happen in the synapses at any time that are at least partially aligned with the gradient, but also have some bias in a constant direction and some random white noise. And so what we do then is we want to look at what happens to the loss function as we update the weights. So we consider weight updates over some time period, delta t, and this delta t actually effectively functions as the learning rate as well then for our characterization of these systems. So we do a second order Taylor series expansion of this update. We get this equation here, and then we can do some math using our knowledge of this weight update algorithm, and that's what we'll be doing in a moment. Now, the thing that we ultimately are interested in, the metric that we want to observe here, is something we're going to call the delta loss. This is basically a measurement of the drop in performance that results from having some bias and variance. So if we consider the difference in loss that we get when we have bias and variance versus the difference in loss that we get when we don't have bias and variance, this is what I'm calling delta loss. And so I'm going to have plots here showing delta loss as a function of bias and variance that you'll see. Now, with our second order expansion, we can then say, okay, what's the expectation of that delta loss value? And what we end up getting is the following. So there's a term that depends on the variance, which is this term here, and specifically it is dependent not just on the variance, but also on the number of parameters in the network, n, and the trace of the Hessian. And then we have three different terms related to the bias here, which I'll unpack a little bit more in a bit, but as you can see, they're dependent both on the Hessian and on the gradient in each of the different terms. So let's start by talking about bias. Okay, so in a very simple case, we can just say that too much bias impairs learning. So if you take even just a simple one-layer linear network and you add some bias in a constant direction to your weight updates, you will impair learning, and not only does it slow learning down, but it also leads to higher plateaus in terms of your final loss value. Now, if we look at that equation a little bit more closely, what we can do is we can take the bias terms here, we can rearrange them a bit into the quadratic term and the linear terms here. And we can see, so we've got in this term a curvature-dependent signal that is independent of the gradient, and which depends on the bias squared. And then we've got another signal here. So this P here represents a whole bunch of stuff from these terms here. So we've got a whole bunch of stuff that's dependent on the direction of the gradient and the curvature, but which is independent of the gradient norm because I've pulled the gradient norm out of the equation here. And the result is that first we can say that with regards to this term, as the gradient grows, so as the norm of the gradient grows, I should say, the drop in performance grows linearly with the bias. Now, that can actually be in both positive and negative directions because it depends on whether that constant direction is aligned with the gradient, as you'll see in a moment. But moreover, what we can say is that the drop in performance also grows with the bias squared, irrespective of the specific direction of the gradient, dependent only on the curvature. So we can see this empirically when we train our networks and we measure delta loss for different levels of bias. And here you can see the linear relationship in these arms. So that's the component that depends on the norm of the gradient. So as the norm of the gradient gets stronger, you have a greater impact of bias. Now, as I noted, that can be both positive and negative. So negative here, sorry, I should say positive indicates that we have a drop in performance. So positive values are bad. Negative values are good. It means we're actually improving performance. And so indeed, you can actually sometimes improve performance with the bias in those instances where it happens to be aligned with the gradient. But critically, because of that b squared term that doesn't depend on the gradient, you're also increasing the intersection of this function as you increase the bias. And the result is that with higher bias, you just get worse performance. And moreover, that can be an even stronger effect for large gradient norms. So you can also see similar effects in a multi-layer nonlinear network, so here a ReLU network. What this means, of course, is that when you look at deeper networks, sometimes the bias is less of an issue in early layers. So here, deeper networks are red, yellow, blue, etc. The purple network with only 2 layers has the worst impact of bias because it's got the strongest gradient norms in it, in fact. So the take-home message for this is that there's always some negative impact of bias, but it is worse when the gradient signal is strong. And that suggests that the brain must avoid bias early in learning or after some change in the environment, and also in particular at output regions that control behavior. Now, moving on to the impact of variance on learning, we can see as well that too much variance can impact learning. This is a log plot though, so it can actually be less of an effect, and you'll see why in a moment. What we can see from looking at this term is, so this was the component of the drop in performance that was due to variance, and we can see that as network size increases, the drop in performance from variance is less of an issue. So variance should not be as much of an issue in bigger networks. And indeed, that's what we see. So when we run our empirical evaluations, the bigger we make our network, the less we get a drop in performance. So that's for wider networks. Here we're increasing the width of the network, but it also holds for deeper networks. So as you take a 2-layer network and then you move to 4-layer or 6-layer, the drop in performance that you get from a certain level of variance is less and less of an issue. And there's also an interaction. As you increase the width, that's also the case. So it means both deeper and wider networks will not be as negatively impacted as by variance. Moreover, what we can show is that if you have a network with sparse activity, for example, ReLU activations, all that's required here is that some of your activities get zeroed out, basically. That's why we're calling it sparse. Then that trace of your Hessian is going to be less than the trace you'd get with a linear network. So that suggests that variance matters less for ReLU networks in this case, but it should also hold for any sparsification of the network activity. And we can see this, in fact. So if you move from a linear network to a ReLU network, for the same sizes of networks, you get less of a drop in performance as a result of introducing variance. So the dotted lines all lie below the solid lines here. Okay, so to wrap up, the take-home message for the variance is that the negative impact of variance is lessened when the network is large and sparse. And it's worth noting that brains are very large and sparse, much larger and much sparser than any of the neural networks we use today. So to conclude, I think, different people react differently sometimes when we talk about learning in the brain with respect to gradients. But part of what we've tried to do here with our analysis is maintain total agnosticism about the nature of the learning algorithm. All we've said is that the brain's updates must somehow follow the gradient to some extent. They can't be orthogonal to it. And that's just true. That's just a fact. As long as the changes in the synaptic connections are not too large, you have to be at least partially aligned with the gradient. Otherwise, you wouldn't get better. You wouldn't start to keep your bike upright. And I think what's interesting about thinking about how the brain or why the brain could have evolved these mechanisms, the fact is that any species that evolved the ability to estimate loss gradients would likely be better at learning than species that didn't. So the more you crunch down your bias and your variance, the better you're going to do, the more you're going to outcompete other species. So it's not completely unreasonable to think that brains have some ways of doing this. And in fact, for those of you who are new to Mila and don't know my research, we've got a whole kind of research program in my lab devoted to understand how brains can do this. But they surely can't do it perfectly. And what our work that I've showed you today suggests is that when we try to look at the mechanisms for what's happening in the brain and how much bias and variance it has in its estimates, we can observe that bias in the learning algorithm is something that brains likely want to avoid, and particularly in regions of controlled behavior and in situations where gradient signals would be large, e.g. early in learning or when some change has occurred in the environment. However, variance in the learning algorithm is potentially more tolerable. This is because brains are very large and sparse. And as we saw, that reduces the impact of variance on the drop in performance. And it's also interesting to note that real synapses in the brain do show a lot of noise. They're just kind of constantly changing irrespective of any learning. And sometimes people wonder how learning can possibly proceed with that noise in synapses. But what our analysis suggests is that in the case where you have this large sparse system, that bit of noise is potentially not quite so bad. So that's that. Thanks everyone for listening. If you're interested in this kind of neuroscience AI intersection, you can follow me on Twitter where I discuss these matters a lot. And yeah, welcome everyone new to Mila. I hope this was an interesting initial talk for you.
Thank you, Blake. I'm doing the clapping for everyone. All right, so we have 3 questions, and in the meantime, Irina, you can start sharing your slides. So the first question was from Joshua. They started discussing it with Arna in the chat, but if Joshua, you want to directly
summarize it. I can summarize the discussion we had and get Blake's response. So the question I was asking was about the bias, that it's you assume it was a constant. I don't think that's realistic. I think a realistic bias from a learning algorithm is going to depend both on the particular example and on the state of the system, the weights, let's say. So now it's not clear, maybe your analysis is still kind of roughly telling us the right thing and it seems reasonable. And Arna was saying, well, if the bias changes with examples and the weights, can't we consider it as noise, like part of variance? And I disagree on that because it's not IID variations, right? So the reason why variance doesn't seem to be causing too much trouble in your case is simply because that noise is canceling out. If you have large number of sources, they sort of, that's what's going on here, I think. So yeah, what do you think?
Yeah, I mean, I don't disagree, Joshua, that there could very well be biases that depend on the current state of the system and depend on the data point. Now, I think there could also be biases that are actually just constant, e.g. there might be something constantly pushing down on the weights for energetic regions and stuff, and that's going to be one of the constraints that you have to consider. So I think our analysis can still speak to that. In an ideal world, I agree with you. It'd be nice to also have an analysis where you have maybe in another term that is dependent upon the data, for example. That makes the math a lot harder, though, of course, and it makes getting intuition on these things a lot harder.
No, I think there's a way to think about it like in a Bayesian way, where you think of, well, we don't know what the bias is, but we can imagine you were learning the learning algorithm, right? So it wouldn't be perfect, and it would have some bias, and you could kind of account for the various possible learning algorithms through a posterior distribution over these learning systems, and then you could see sample from the various bias functions basically.
Yep.
Implicitly.
Yep, that's an interesting idea. Yeah, we should chat later.
Yep.
Right. Next question was from Tsuji.
Jay also had a question.
Yeah.
Okay. Well, I just wanted to point out that from what I remember in your equations, noise is having a definite negative effect, right, on your descent of the loss. But is that really true? I mean, you might imagine that noise might help with things like exploration, generalization. So because you're only considering the descent on the training loss, right? So maybe is that why it's zero or greater negative impact?
Right. Yeah. So I mean, indeed, you're right. We can also expect that the noise might actually be just straight up beneficial for test loss sometimes. Now, I think that it's still important to consider just the drop on the training loss, because when you look at the capabilities of a human or an animal, they can do quite well on their training data, right? So you do want to ask, how is it that we can achieve good performance on the data we've seen? There's then the additional question of, well, might there be other ways in which this noise might be helpful, even if it impairs a little bit your drop in loss on the training data? Could it help with generalization? Certainly. I expect that it very well could, in fact.
Okay. Because in the limit of minimizing the training loss, that's just memorization. So I mean, you might actually not want to completely minimize the training loss. At least empirically, that's why we have things like early stopping, right?
Well, but you want to be able to minimize the training loss effectively, is the point. Okay, so you're right that you don't necessarily want to completely eliminate the training loss always, because that might mean that you're overfitting to some extent. But you definitely need a system that can effectively minimize the training loss, which in and of itself, when you're looking at a system with a lot of noise, is not a guarantee.
Right. Thank you.
Yeah, cheers.
All right, perfect. And so we're gonna take the last question after the third talk.
Sounds good.
Perfect. Irina, whenever you're ready, the floor is yours.
Okay, the only thing, I won't be able to see the chat when presenting.
Oh, no worries. No worries.
Okay, and the second quick question, do you see the full screen right now?
Yes.
Okay, great. Okay, so yeah, I guess I'll start then. So, well, hi everyone, and yeah, I'm working at Mila on the various topics related to continual learning and then more generally trying to make AI systems more broad or versatile in presence of various changing tasks. That's kind of one of the current kind of trends in the field because, well, I'll talk about that a bit in more detail why not having that is a problem. And also robustness is another important topic. I'll talk about that and the issues with fragile systems. And in general, I mean, there are some recent developments and there are many discussions and arguments about what would be the best path to creating, well, artificial general intelligence. And perhaps there are multiple ways to get there. So at least I will briefly mention some recent developments in terms of large-scale models, large-scale pre-trained models, many of you might have heard about, and some kind of research here at Mila that we're trying to do in this direction as well. So, but I only have 20 minutes and lots of slides. I'll try to go really fast. Okay. Oops. Okay, so I mean, needless to say, we're all impressed by recent advances in AI. We know all about beating human champions in different games and painting pictures with GANs and so on and so forth. So needless to say, those advances are impressive. However, I think the field still recognizes one of the big challenges is the ability to make systems truly versatile. They don't have to beat human champions, but just like a regular human, it would be nice if you can learn to play Go or chess and paint a little bit and then learn another language. And you don't have to be perfect at that, but it would be nice if you were more human-like in terms of being more versatile. And that's not quite yet what the systems can do, although with, as I mentioned, recent developments in training unsupervised large-scale models, they are getting better and better at few-shot learning. I'll mention that later on. And I think we kind of should start focusing on those and try to build on top of them. But going back to the issues that we try to see if we can fix that still kind of differentiate those systems from what a regular human will be able to do. Robustness is another well-recognized issue. Adversarial robustness is just kind of one example of that. The classical pictures from papers where people show how a little bit of adversarial perturbation of an image will not really be noticed by human eye and will confuse system quite a bit into totally misclassifying those samples. Even if these perturbations are not adversarial, but simply environment changes, or it's like some statistical changes due to a new task, but you believe that there is something in common between those data distributions and you'd like to capture that. For example, you want to classify animals and your training data set mainly consists of pictures of cows on the green background. It's known that kind of existing algorithms typically will learn to rely on spurious features because they're easier, such as background. So basically, shortcut feature issue is a big problem in learning deep nets. And the question is, how do you make sure that it's not the shortcut they will rely on, but the true like shape property of the animal? Because if you switch from this type of environment to something like cows on the beach, again, the classical example, unless you do something about that, the system will tend to misclassify that poor cow as something else because it's not a green pasture that the cow is on. It's so-called area of out-of-distribution generalization, though the word out-of-distribution remains to be defined more precisely, and we have some interesting discussions on that. But I'll touch upon that briefly in a minute. So this kind of different issues with robustness and generalization in more general sense, or kind of being versatile, are usually pointed out. What is also sometimes quite often pointed out is this whole question, which is an open question. I'm not claiming that it's kind of true or not. But the hypothesis is that perhaps existing so-called second-generation neural networks, which are essentially just statistical models with a fixed set of parameters that you feed from data, and once you converge to this set of parameters, you call this your artificial intelligent agent. They might be much more limited in terms of what information they can represent as compared to human-animal brains, which, as we can see from various data we collect, and just in reality, they are never static statistical models with fixed set of parameters. They are constantly kind of active, communicating without any input provided. Like if you have no input provided to the system still constantly changes, and activations trigger other activations in the brain. So it's like dynamics of the system may be something that allows it to encode information about the world that perhaps the classical second-generation neural network might not be able to do, or at least it might not be able to do it at the same scale. So there is this hypothesis about third-generation neural nets as kind of dynamical systems, and the time coding besides rate or space coding that might be needed to encode information more effectively. Again, that's an interesting question to explore, but this is all type of questions we ask ourselves, trying to figure out what do we need to do if we want to get as close as possible to natural intelligence. Anyway, so that's essentially what I was saying. You definitely need to go from narrow to broad, from brittle to robust, and perhaps, question mark, you may need more neuro-inspired type of models, or alternatively, there is a scaling hypothesis that you might be just fine with existing class of neural networks, but if you scale it with the amount of data, model size, and compute, you might just get emergent properties of the system. So that's a very hot developing field, and we'll see how things will develop. Okay, just to briefly give you an idea what I meant by robustness, the classical examples, as I mentioned, when you have image, you add some adversarial perturbation to that, some kind of innocently looking noise that doesn't change your perception, but it changes deep net perception drastically. So there is a whole field of adversarial robustness, as you know, and there are many approaches to handling this type of situations to make systems more robust. I'm just giving, of course, an example from our recent work, by the way, with Blake and Poya Bashivan, who are both at McGill, and several more people. The paper is on archive and currently in submission, but briefly the idea might be that sometimes it might be more advantageous to focus not at the robustness of the system in terms of its final performance, say as classifier, but rather focus on the robustness of representations you're learning. And you can go about that in different ways, where essentially introducing adversarial game between representation learner and a discriminator of representations belonging to clean images versus perturbed adversarial images. That game can actually help you learn robust representations, which happen to be better in terms of performance than kind of trying to train the model with the end goal of the classification being robust. So, and again, just a very quick picture. I mean, there is much more in the paper, but you can kind of see here that if you compare this representation robustness focused approach versus existing state of art and approaches that focus more on the robustness of a final result, you see that this green line becomes much more robust with increasing strengths of a particular adversarial attack. In this case, it's so-called PGD. Anyway, so it seems to be worth focusing on making representations robust rather than trying to optimize kind of the final result. Just one example. In terms of the robustness to statistical perturbations or changing environments or data distributions, while assuming that there is still certain certain so-called independent mechanism producing the data in common, in this case, shape of the animal. In this area, there is lots of work. It's actually a very hot topic in the past couple of years, all starting with this 2019 paper on invariant risk minimization. Again, there is a long history even before that, but the brief idea is that if we assume that you can extract a set of features that have like truly robust invariant causal relationship with the label, then you can kind of formulate a problem that let's try to find a mapping to that set of features so that on top of them you can have exactly same optimal linear classifier across different perturbations of data across different so-called environments. And that's a RAM principle, and it's one way to try and kind of force your model to be more robust to perturbations in the data as long as the common mechanism is shared. Anyways, there is lots of work, follow-up work on that, and lots of also theoretical work studying properties of this type of approaches because they only work in certain settings and do not work in others. And understanding what works when and where is still an open direction. So there is also one recent paper I wanted to point out that Kartik Ahuja, who is a postdoc at Mila with me and Joshua and Ioannis, he kind of worked on understanding when IRM works and when it doesn't, and what is necessary perhaps to add to make it work in scenarios. For example, linear classification actually requires stronger assumptions than regression, the original setting of IRM paper, and you may need extra regularizers to find this kind of invariant predictor. And for example, information bottleneck type of regularizers, as shown in that paper, can help you actually find the invariant mechanism, while IRM on its own might not be able to do that. Anyway, so there's no time to dig into details, and I'm just giving you a flavor of things that one can kind of explore in the direction of improving robustness. There is also a recent line of work on other type of approaches to enforcing robustness to data perturbations, and it's so-called invariant learning consistency. That's work from Bernard Schölkopf's group, and again, I don't have time to go into details, but be happy to talk to you afterwards on Slack or by email, and you're welcome to look at the paper. The main idea there is that you may want to modify your learning algorithm so that it will be guided towards solutions or basically local minima that are simultaneously good for multiple varying environments or data sets, instead of just trying to optimize the average loss. And they show examples where this is advantageous, and one way to approach that could be to impose certain, say, mask on the gradient so that you only choose directions which are consistent, which are directions of improvement for multiple different data points and data sets. And if there is too much disagreement on this direction across different data sets, you just do not go there. It's coordinate-wise approach. But there are some issues, again, I don't go into all details, there are some issues with this approach, as usual with everything, and it can be improved further. And basically, so there is some serious dependence on the, for example, initialization with this approach. There are so-called dead zones which you can get into where you have zero gradients and you will not be able to escape. And to fix that, anyway, we try different things. There is, again, another archive paper that you're welcome to look at where the smoothed end masks seem to help with those issues. But of course, I mean, there is no perfect method. We all know about no free lunch theorem. The methods still seem to be doing better than the original end mask, and pretty much any method in current so-called domain bed framework, which is a framework containing pretty much all the recent invariant predictor type of approaches, IRM, and so on and so forth. It seemed to be best in terms of colored NIST, which is standard benchmark for this type of studies. But it still doesn't work on some other benchmarks, and still kind of interesting question how to come up with approach that avoids those pitfalls and kind of tries to kind of generalize better on as many data sets as possible, including some practical ones. So anyway, so it's work in progress. Okay, since I'm kind of running out of time, I just want to briefly mention that this type of approaches imposing robustness across different data sets are also quite, can be quite useful in applications such as federated learning, where you have multiple clients on which you have separate data sets, and those cannot be shared with a server or with each other due to various constraints such as privacy or simply like other constraints. For example, the data sets could belong to different hospitals and their patient data sets, and yet you want to learn a joint model across them. So doing ILC or its improvements in federated learning setting can be shown to provide better models as well, more robust one, and generalizing better to new previously unseen data. Again, it's ongoing work in the group. There is a workshop paper on that. And finally, as I mentioned, not only we're interested in systems that can be versatile with respect to multiple different tasks, you also want those systems to be able to learn continually when the tasks come sequentially, and therefore it's more challenging kind of setting because you don't have all these tasks and all the data available all the time. And even if you store all of them, then accessing those samples and retraining your model in real time is not practical. So yeah, I'm kind of running out of time. I just wanted to give you the idea of what continual learning setting is about. Essentially, it is online, non-stationary learning setting, where you have a stream of data, and the data are not IAD, not independent identically distributed samples. They're only locally IAD within subsets of data or tasks, and those keep changing with the learner, sometimes aware, but often unaware of where the task boundary occurs. It relates to multiple fields in machine learning that you may know about. It closely relates to multitask learning, well, because there are multiple data sets, but unlike multitask, it has to happen in online setting. It relates to transfer learning, but none of those really face problems that continual learning faces, because continual learning tries to learn all the new data sets while performing well, or at least being able to remember how to perform well very quickly what it learned before. So transfer learning and domain adaptation and meta learning, all related to continual learning, but all in a sense less challenging than continual learning setting. And essentially the main challenge is that you would like to ideally optimize your risk or expected loss across all the data sets you've seen so far, but you don't have access to them, and you need to somehow represent them, whether through representative samples in a regional space or in the latent space or in some other form of memory. You would like to capture the information from the previous data sets while keep adapting to the new ones. Anyway, so catastrophic forgetting is a classical problem in this field, which means that if you don't do something about that and just keep applying SGD to learning from this non-stationary stream, you will quickly adapt to new data, but your performance on the old data will keep degrading, and that's what forgetting is. Anyway, so there is more on that, which I won't go into right now. We have the class on continual learning, and it's online with more lectures. There is also ICML tutorial on that. There are several papers that try to introduce unifying framework for continual learning and try to essentially implement as much as possible those properties from the desired list of properties. There is also a recent survey on continual reinforcement learning that we have out there. It's a field on its own, more challenging than just the supervised continual learning. You're welcome to, again, look at that in the archive. There is a tool, the framework called Sequoia, developed by Fabrice Normandin and Massimo and many others here, which essentially tries to organize different settings, not just for continual learning, but for other type of machine learning problem formulations, and provides you with a common set of benchmarks. So it makes evaluation of new algorithms much more convenient and easier. And I guess I just want to skip to more recent developments. As many of you might have heard about that, there was a recent expansion of number of papers on neural scaling laws, and the question there is whether with scaling in terms of model size, data, and compute, say, can you solve problems such as continual learning, and what kind of problems can be solved this way, and what does it mean to solve them? And just to give you a very quick gist of that, the main message, the main result there is that if you increase the amount of compute available, the amount of data you train from, in this case, essentially assuming online training, just like in continual learning setting, because you say GPT-3, the natural language system, was trained on most of the internet, and there are other systems such as Clip and DALL-E trained on many images. So basically you don't have even opportunity to do multiple epochs. If you train it in this online fashion and increase data set size, or you also increase the number of parameters. If you fix that one variable, say you fix data set size, and you allow yourself to play with model size and compute, choose the best result, and plot on log-log scale how your performance changes. You seem to be able to fit straight lines, which essentially mean power law distribution of the performance with respect to those parameters, such as compute, data set size, and size of the model. The importance of that, again, I don't have much time, but the importance of that is that you don't have to have humongous compute to benefit from neural scaling laws, because if I skip a few things, I won't be able to cover. What I wanted to show is that if you can extrapolate the behavior of your favored algorithm or architecture, you can see, and that's important to know, that, for example, in this case, convolutional networks in comparison with visual transformers at low scale outperform transformers, but then the situation reverses because transformers have better scaling, they will have better exponent than convolutional networks in this case, and so on and so forth. So knowing the parameters of the scaling law curve is very powerful, because you can predict which method will work better in the future, provided that you will have more data, can scale models, and have more compute. And that basically tells you where to invest your effort in, and what will be probably more successful in the future. As to whether you can solve continual learning with scaling, there are promising results people are showing, but in a sense only on finite number of tasks. And the question remains, what happens if you have infinite stream of different tasks of high complexity? I believe that one will not only focus on scaling, but rather on trade-off between how you scale model capacity versus how your input stream complexity scales, and what do you need to capture that information. And it may require lots of scaling in standard set of models and maybe growth of those models, It may potentially require a different type of models that, as I was mentioning, more like brains incorporate temporal coding into them, so they actually work as dynamical systems, and changes in the dynamics also contain lots of information, but that's more like an open hypothesis. I think that scaling standard models can go a long way. Okay, I think I need to, yeah. But okay, I'm pretty much done. Yeah, I don't have. Yeah, I think I can stop here.
Cool. All right. Thanks, Irina. We're gonna directly transition to Danilo's talk, and yeah, keep questions for. Feel free to ask your questions directly in the chat in the meantime. Thanks again, Irina.
Okay, thanks. So I'm not sharing screen anymore, so I think Danilo can.
Yeah.
All right. Everybody can see my screen?
Yes.
Right. I go right in?
Yeah, you can start, Danilo.
Okay. All right. So my name is Danilo Stock. I'm here for about 2 years now, arrived right before the pandemic. And ever since I started research in neuroscience roughly 10 years ago, I was really fascinated by what makes the human brain special compared to other species. And that's, of course, a lot related to the deepest biological neural network layers of the human brain. And in this talk, I'll give some perspectives how this may be interestingly considered from a Markov decision process perspective. So why is the so-called default mode network so special? So the default mode network is a couple of brain regions in the higher association cortex in the human brain, of which we know that they expanded more than a 30-fold in volume compared to our closest monkey ancestors. Okay, so it's hard to deny that there's something special about this set of brain regions. They consume by far most energy in the brain. And we also think that they really subserve some of the most advanced, potentially human-defining classes of cognitive processes that we humans can do, such as introspecting into somebody else's mind, imagining possible futures, considering hypothetical events, counterfactual reasoning, moral cognition, all these very advanced type of processing, they are very closely related to neural processing that's going on in this so-called default mode network, which is furthest away from sensory input processing. Okay, so if you count the number of neuron switches that you need to get to a particular part of the brain, starting from early sensory cortices, the default mode network is really the last stage. And this is why, if you did consider it from a deep learning type of perspective, it would really be the last layers of the neural processing hierarchy, potentially. It is also at the crossroads of pretty much all major psychiatric disorders. This is particularly interesting to us from this anthropological perspective, because we don't really know to what extent animals like cats, dogs, mice experience major psychiatric disorders, so they may be human-specific to a certain degree. So to some extent, the part of the cortex that allows these amazing cognitive feats may also have a negative side of the coin, which may be some diseases that other species maybe do not experience to the same degree. So what's going to lead to this reward and a reinforcement type of perspective of what this higher association cortex globally may be doing is really this piece of empirical evidence here. So what you see there is in 40,000 people from the UK Biobank cohort, which is the largest biomedical data set, we show that the nucleus accumbens, which is at the core of the reward circuitry in humans, is very closely coupled structurally with all subregions of what I called the default mode network before. That is surprising to a large part of the neuroscience community in our perspective, because they are largely disconnected literatures. Okay, so there's more than 1,000 papers per year that talk about a human default network, but they typically do not mention the reward circuitry or the nucleus accumbens. And in the reward processing literature in humans, they typically also do not really talk about the higher association cortex. However, we explain a large fraction of the variation out of sample between these two systems. And this makes us think, well, maybe the higher association cortex is at the core of a general control process for the organism to tackle problems in the environment, not only in the here and now, but extrapolating from the past into the future. And what's going to be a guiding thought is what may justify these very costly extensions of the monkey brain in the human species. One of the best adaptations that we can think of would be to have probabilistic versions of the past to extrapolate into possible futures, which could then allow to adapt better to challenges in the present. And that's what we call the Markov decision process equivalent of the default mode network. And that's worked together also with Guillaume Dumas here at Mila. So what's important to emphasize is that we are trying to come up with a framework of how these deepest biological network layers may be processing information and subserve several of these human defining capacities. I gave examples, but it also includes, of course, language processing, for example. So can we come up with a framework that really explains the existing cognitive theories as special cases? So here's a general quote that already motivates this perspective. So it has been proposed that the human brain's energy budget is maybe largely dedicated to the development and maintenance of a probabilistic model of anticipated events. And that is what the person said, Marcus Reckel, who actually discovered the default mode network that we didn't really know about even 20 years ago. So what I invite you to think about is maybe there's value in really considering these highest top level neural processing layers from a perspective where we have iterative improvements by action policies and value matrices that get improved over time based on feedback that's received from the environment, which is a general view of the reinforcement learning community. But more specifically, why is the Markov decision process particularly interesting? And one normative argument is that various types of intelligent behavior in animals and humans have successfully been modeled with the Markov decision process. And it's stock market behavior, migration flocking behavior in birds. So this is why we think that it is natural to also think about whether some of the most advanced parts of the human brain may perhaps be interestingly framed and considered and predicted based on this modeling framework. So as I'm sure I don't have to explain to this audience, the idea is that you are in a certain state at a certain point in time, discrete time, and based on the states and your current value considerations of the environment, you take one of various actions in the action portfolio. And the Bellman equation here at the bottom, what's important about it is that it has this iterative deconstruction of reward in different steps into the future. And we think that this is a key aspect of why it is interesting to consider the high association cortex from a Markov decision process perspective. For one, because it really gives some insight into how extrapolation from the past and consideration of the future may guide decision-making in the present. So the cognitive neuroscience community made some steps into this direction. I'll just give one example here from the prefrontal cortex, where people were thinking about maybe a general processing principle of what this part of the brain is doing is related to the goal tree sequence process, cognitive branching, sub-goal processing, sub-goal scheduling. So those are all ideas that the neuroscience community has been talking about, but maybe we can frame it from this broader perspective, from a more formal perspective. And this is what helps us to take decisions. So if we now take aspects of the Markov decision process framework and put them in order onto what the neuroscience community thinks these different parts of this major network are doing, this is one of the perspectives of what we get. I'm not saying that the deepest biological neural network layers are equivalent with this process. And I'm also not saying that these equations exactly describe what these parts of the brain are exclusively or uniquely doing. All that I'm saying is that we have poor understanding, and maybe humans haven't even evolved the semantic notions to adequately describe what the most complex processes potentially of the human brain are doing. And so maybe we can use this modeling engineering type of framework to at least have a new vocabulary and a more general framework that implements these cognitive theories as special cases. So just some examples. Cognitive neuroscience thinks that maybe a lot of processing in the brain can be explained by predictive coding. That's the idea that there's a neural processing hierarchy. At each stage, we make predictions that get considered in the next downstream processing layers, and then we have back projections into the earlier ones, and that is how plasticity is happening. So if you take a framework such as it has been used in AlphaGo, for example, it actually encapsulates all these ideas that predictive coding are about and extends them even further. Another general idea of how cognitive neuroscience thought to explain these deepest neural circuits of the human brain is that maybe we are constantly making analogies and semantic inferences of aspects in our environment. And this is how we can do higher level human defining processing. The last idea is the sentinel hypothesis, where people think that the most valuable evolutionary adaptation to the environment is to be better at detecting what's valuable in the environment. And this is partly why some people think that social interactions, social cues are some of the most valuable pieces of information in our environments. But we argue that if you adopt this discrete latent state action policy value matrix framework, value in the environment that comes from social sources can very well be explained, and it doesn't need to be exclusive to social content, as some of these theories from the cognitive neuroscience community have been proposing. So just very quick, what's attractive about this account is it explains several aspects like time horizon, neuroplasticity, hierarchical processing, and what is actually the goal of a particular suggestion of what this process, what these circuits are doing. It can explain several of these things at the same time, which is not the case, in our opinion, for several of the dominating cognitive theories. Okay, so just to summarize, what we are proposing is a candidate answer to the admittedly ambitious question: what may be the function in the deepest layers of the neural processing hierarchy of the human brain, which have recently expanded drastically in evolution and that by far consume the highest energy? And we're saying it may be the probabilistic recombination of information from the past to make predictions about the future to guide behavior in the present. And that, for example, may be the reason why creativity is important. And exact memory in humans may have been disfavored in evolution. So Enning, for example, is making amazing steps in this direction in our lab, who puts these theories to the test in empirical studies where we look at the fault network and the reward circuitry, one of the most naturalistic environments in humans that we have, and that's movie watching. And we use extensions of hidden Markov models to do that. All right. And with that, I'm done, and I hope that was interesting for the audience.
All right, many thanks, Danilo. Okay, so what I'm gonna do is that I'm gonna stop the recording so that we can directly transition to a more informal question period. For those who have to leave, thanks again for joining us, and we'll see you next week for another Prof Series talk. It will be Xu GC, who will share his thoughts on program reasoning, if I'm not wrong. And thanks again, Blake, Irina, and Danilo for this first Spotlight Prof Series edition.